Hello there and welcome to my channel. The world beyond your walls can feel hectic and overwhelming, but here everything softens and slows. Tonight we're not looking out at mountains, rivers, or a shimmering night sky. Instead, we're drifting into a secret domain where a lone photon can glide like a wave yet respond like a particle. Where atoms can connect across unimaginable distances and even the emptiest vacuum quietly hums with energy. We'll move gently through quantum fields, teleporting particles, and moments where simply observing can influence what becomes real. Some of what you hear tonight might confuse you. Some may linger in your mind, like a fading dream you're sure you felt but can't quite put into words. And before we begin, if these calm, curious wanderings help you settle down or give you a peaceful way to end your evening, consider liking and subscribing. Or just share a thought in the comments below. It helps others find their way here too, one restful seeker at a time. Now if you're ready, let's begin. The laws of physics behave very differently on incredibly small scales. In our daily world, physics feels steady and reliable. Apples drop, clocks tick, and light seems to travel in straight paths. But shrink your perspective to the scale of atoms, and those familiar rules begin to bend. In the quantum realm, particles rarely follow fixed trajectories. They move according to probabilities, acting more like soft, misty clouds than tiny solid points. Causes and effects refuse to line up in the tidy, orderly way we expect. Events may unfold without obvious reasons, and often multiple outcomes exist together until something compels a decision. This unusual transition, from certainty to possibility, is what makes quantum physics feel like a hidden universe woven inside our own. It's not that the everyday rules collapse. It's that they were never the full story. Beneath them is a stranger, gentler framework that holds everything in place in ways we're only just beginning to uncover. Quantum physics governs a world unlike anything we witness firsthand. Most of us will never actually see the quantum realm. Its tiniest components are far smaller than the wavelength of visible light, leaving them forever concealed from human sight. Yet their mysterious behavior shapes everything we breathe, touch, and ultimately become. In this invisible domain, particles drift like spreading ripples, appear for the briefest flashes, and sometimes behave as if they're in multiple locations at once. The rules here are expressed in mathematics so unusual that even experienced physicists admit they use the formulas without claiming to completely understand them. This isn't just a miniature copy of our world. It's an entirely different one, running on principles that challenge our everyday intuition. And without this unseen realm quietly carrying out its patterns, the visible universe, including all of us, could never exist. Energy is not a smooth continuum. It arrives in tiny packets. In the late 1800s, scientists believed energy flowed evenly, like water pouring steadily from a tap. Then came the surprise. Under certain conditions, it isn't smooth at all. Light, heat, and other forms of energy are made of tiny, indivisible quanta. A quantum is the smallest unit of energy a system can gain or release, like the smallest coin in the universe's currency. This discovery, born from studying how light interacts with matter, upended centuries of assumptions. It clarified why heated objects glow with specific colors, why atoms absorb and emit light in thin spectral bands, and why energy sometimes appears in sudden jumps instead of gentle, continuous streams. Without this idea, quantization, modern technology from lasers to computers would be impossible, and the doorway to quantum theory might never have opened. Matter can flow like a wave yet strike like a particle. It sounds contradictory. How can something behave as both a wave and a particle? Yet that is exactly how quantum objects act. Shine light through two narrow slits, and it spreads into rippling interference patterns, a signature of waves. But detect the light photon by photon, and each one hits a single point like a tiny pellet. Electrons, atoms, and even certain large molecules do the same. This wave-particle duality shows that particles don't travel as miniature billiard balls, but as probability clouds stretched across space until they're measured, then their wave-like spread collapses into a single spot. This odd dual nature isn't merely a curiosity. It forms the core of quantum mechanics. It reveals that what feels solid and localized is actually part of a broader, fluid pattern that only sharpens when observed. Simply watching can alter how reality plays out. In the quantum world, observation is never passive. The act of measuring a particle can alter its state. In the famous double-slit experiment, photons or electrons create wave-like patterns when unobserved, but shift to particle-like behavior when their paths are monitored. It's as if nature responds to our attention, though physicists attribute it to the unavoidable interaction between the measuring device and the system itself. Still, the questions run deep. If every measurement changes reality, then what is reality before we measure? Is the world suspended in a hazy in-between until something forces a decision? Whether viewed as a physical effect or a philosophical mystery, the idea that observation changes the outcome remains one of the most astonishing truths in quantum mechanics. One that has intrigued and unsettled scientists for more than a century. Nature prevents us from knowing everything about a particle. Classical physics insisted that with perfect measurements, you could know a system completely, its position, its speed, its exact future path. Quantum mechanics says otherwise. The Heisenberg uncertainty principle states that there are strict limits to what can be known simultaneously. The more precisely you determine a particle's location, the less precisely you can know its momentum, and the reverse is equally true. This isn't a flaw in our tools. It is a built-in rule of nature. Particles simply do not possess exact values for certain paired properties at the same time. The uncertainty is genuine and unavoidable. This means that on the quantum scale, the future can never be predicted perfectly. We can only calculate probabilities. A shift in worldview that reshaped science and challenged our deepest beliefs about determinism. A particle can exist in many states at once. Superposition is one of the most baffling ideas in quantum physics. The notion that a particle can occupy multiple states or locations simultaneously. An electron can spin up and down at the same moment, or a photon can follow several paths at once. These states exist in a fragile balance described by a mathematical wave function. Only when a measurement occurs does the particle settle on a single result, and the superposition dissolves. This isn't hypothetical. Experiments have confirmed it countless times. Quantum computers rely on superposition to perform vast numbers of calculations simultaneously, granting them extraordinary potential strength. In everyday life, we never witness superposition directly because it collapses instantly when we interact with it. Yet at the quantum scale, it is the rule, a reminder that our familiar world is just one realized outcome pulled from a cloud of overlapping possibilities. Reality is built from probabilities rather than certainties. In the quantum domain, nothing is determined until it occurs. A particle's position, momentum, or spin is not fixed ahead of time. It is described by a set of possible outcomes. These possibilities live inside the particle's wave function, which evolves smoothly until an interaction or measurement takes place. Only then does a single outcome appear, chosen, seemingly at random, from the available options. This probabilistic nature isn't due to missing information. It is fundamental to the universe itself. Even with complete knowledge of the wave function, you can predict only likelihoods, never absolute guarantees. This idea unsettled many physicists, including Einstein, who famously remarked, "God does not play dice with the universe." But more than 100 years of experiments have revealed that at the tiniest scales, probability isn't a symptom of missing information. It is the nature of reality itself. How these possibilities collapse into a single event remains a profound mystery. We know a quantum system can exist in many potential states at once, and that measurement somehow narrows those possibilities into one outcome. But exactly how this collapse occurs, or whether it happens at all, remains one of physics' greatest riddles. Some interpretations argue collapse is a physical process sparked by observation. Others suggest that every possibility unfolds, but we only witness one branch of an immense multiverse. Another idea proposes that collapse is merely an illusion, and the wave function never truly shrinks. After decades of debate, no agreement has been reached. What is clear is that this moment, the shift from countless possibilities to a single reality, lies at the heart of how we experience the world. Understanding it may require not only new physics, but a deeper understanding of consciousness and the boundaries of what we can know. Schrödinger's cat is both alive and dead, until you look. In 1935, physicist Erwin Schrödinger created a thought experiment to reveal how bizarre quantum superposition becomes when applied to everyday objects. Picture a cat inside a sealed box with a mechanism that has a 50-50 chance of releasing poison depending on the decay of a single atom. Quantum theory says that atom sits in a superposition of decayed and not decayed until observed. And so, in principle, the cat is simultaneously alive and dead. Only when the box is opened does the superposition collapse into one result. Schrödinger never intended for anyone to take this literally for real cats. He designed it to expose how absurd quantum rules appear at macroscopic scales. Yet his legendary cat remains one of the simplest and most enduring images for grasping the strangeness of quantum mechanics. Two particles can share the same existence across space. Entanglement is one of quantum mechanics' most astonishing features, a phenomenon where two particles become so deeply connected that their states can no longer be separated. Measure one and the other's properties lock into place instantly, no matter how far apart they are. It's as though they aren't two objects at all, but one unified system stretched across distance. This link doesn't weaken with space, and it doesn't rely on signals traveling in any ordinary sense. Once entangled, particles share a joint identity. Physicists have created entangled pairs using photons, electrons, and even clusters of atoms. The connection is delicate, easily disrupted by outside influence. But when it survives, it hints at a deeper layer of reality, one where separation itself may be an illusion and the universe is far more intertwined than it appears. Touch one particle here and another responds instantly far away. If you take two entangled particles and move them to opposite sides of the planet, something remarkable occurs. Measuring one immediately fixes the state of the other. This happens even when they're so distant that light, the universe's speed limit, couldn't send a message between them in time. It's not that information outruns light. Instead, the particles never had independent states to begin with. In a meaningful sense, they are a single entity. This instantaneous correlation has been verified repeatedly in experiments, across distances ranging from a few meters to hundreds of kilometers. The results always align with quantum theory's predictions, no matter how counterintuitive they appear. It serves as a reminder that our everyday ideas of cause, effect, and distance may not hold in nature's deepest layers. Even Einstein was unsettled by this strange quantum connection. Albert Einstein famously rejected the idea of entanglement. He called it spooky action at a distance, convinced it must reflect an incomplete description of reality. In his view, there had to be hidden variables, unseen factors that could explain the strange coordination between particles without invoking faster-than-light effects. Together with Boris Podolsky and Nathan Rosen, he introduced a thought experiment in 1935, now known as the EPR paradox, to challenge quantum mechanics. They argued that if the theory was correct, it implied either impossible communication between distant objects or that particles lacked definite properties until measured. Both ideas felt absurd. Decades later, experiments showed that entanglement is real and cannot be explained by hidden variables alone. Ironically, Einstein's own objection helped spark the research that proved quantum mechanics' most mysterious feature. For years, entanglement remained a theoretical curiosity. Then, beginning in the 1970s, physicists created experiments to test it directly. Using pairs of photons, they studied the correlations between them and compared the data to quantum predictions versus classical hidden variable models. The results were decisive: quantum mechanics won. Since then, tests have become more precise, closing loopholes and increasing the distances between entangled particles. In 2017, scientists beamed entangled photons between ground stations and a satellite, confirming the effect across more than 1,000 kilometers. Each demonstration strengthens the conclusion: entanglement isn't a lab quirk. It is a fundamental property of the universe, and as strange as it feels, nature allows this perfect connection with no visible link at all. No hidden mechanism explains these uncanny correlations. Einstein hoped that entanglement could be accounted for by hidden variables, secret information carried by particles that predetermined their behavior. But in the 1960s, physicist John Bell created a mathematical test to determine whether such variables could exist. His result, Bell's theorem, showed that if hidden variables were real, entangled particles would only exhibit limited types of correlations. Quantum mechanics, however, predicted stronger ones, and experiments consistently confirmed the quantum results. This means no theory based solely on hidden, local information can fully explain what's happening. These connections may weaken when they're disturbed, yet new ones constantly emerge as particles encounter one another. The notion that reality is woven together in this invisible way challenges the old picture of a universe made of lonely points scattered through empty space. Instead, everything might be part of one continuous quantum dialogue, expressed in the shared language of entanglement. Entangled particles can hold on to their connection even when the odds seem impossible. Entanglement itself is fragile. Heat, noise, or environmental interference can easily disrupt it. But under certain conditions, it can endure in unexpectedly powerful ways. Systems such as superconductors and Bose-Einstein condensates can maintain huge collections of particles in entangled states that last far longer than expected. Even in the messy, chaotic world outside laboratory walls, scientists have detected faint traces of entanglement between particles separated by remarkable distances. This surprising durability turns entanglement from a delicate oddity into a potential cornerstone for future technologies. If we learn how to shield and guide it, we may use these lasting quantum links to drive revolutionary communication, computing, and sensing systems that could change how we exchange and understand information. Electrons are unimaginably tiny, yet they spread out like mist. An electron, one of the most familiar subatomic particles, flows through electric circuits, binds atoms, and shapes the chemistry that makes life possible. But when researchers try to measure its size, they discover something astonishing. It behaves as though it has no inner structure and no measurable diameter at all. And yet, it refuses to act like a single sharp point. Instead, its presence appears blurred into a cloud of probability circling the nucleus, arranged in patterns defined by quantum laws. This electron cloud isn't a physical vapor. It's a guide to where the electron is most likely to appear. One moment it may be close to the nucleus, the next it may be far away. And you cannot know precisely where until you observe it. This dual personality, both point-like and spread out, is a perfect illustration of how quantum particles challenge everything we expect from everyday experience. Weightless photons can still push the world around. Photons, the particles of light, carry no mass, yet they hold energy and momentum. Because of this, they can apply pressure when they strike an object, a phenomenon called radiation pressure. In space, where nothing slows motion, even this tiny nudge can create enormous changes over long distances. Sunlight can gradually shift the orbits of dust particles, small asteroids, and even spacecraft. Engineers have built solar sails, huge mirror-like sheets that ride on the momentum of sunlight, requiring no fuel whatsoever. On microscopic scales, concentrated beams of light can grab and move tiny objects using optical tweezers, a tool widely used in nanotechnology and biology. That something with no rest mass can still push matter is one of the most extraordinary and practical gifts of light. Billions of ghost-like neutrinos pass straight through you each second. In every moment, without your awareness, countless neutrinos are streaming through your body. These almost massless particles are produced in staggering numbers by the sun, distant stars, exploding supernovas, and even radioactive decay deep within Earth's crust. Neutrinos interact so weakly with matter that they glide through entire planets as if they were nothing but open space. Trillions of them move through the Earth, and through you, at any given moment. Yet detecting even one is incredibly challenging. Enormous underground detectors filled with ultrapure fluids or ancient ice wait for the rare instant when a neutrino strikes an atom. Studying these elusive particles reveals clues about how stars burn, how the universe has unfolded, and whether matter and antimatter are perfect opposites. Invisible and almost untouchable, neutrinos prove that the universe is flooded with hidden motion and subtle energy we barely recognize. Quarks are permanently confined in pairs or trios. Quarks form the core components of protons and neutrons, and thus of nearly all matter we can see. But unlike electrons, quarks are never observed on their own. They are imprisoned by the strong nuclear force, carried by particles called gluons. This force becomes stronger the farther quarks are pulled apart, like stretching a rubber band that pulls back harder as it lengthens. Try to separate quarks, and the energy you add eventually transforms into new quark pairs, which instantly lock together to form entirely new particles. This phenomenon, known as confinement, means quarks are permanently locked together in pairs called mesons or trios called baryons. It's as though nature has declared that quarks can never wander alone. They exist only as pieces of a larger whole, bound deep within the nucleus of every atom. Gluons create the strongest bonds known in the cosmos. The strong nuclear force is the most powerful of the four fundamental forces, and gluons are the messengers that carry it. Their name comes from their role, gluing quarks together to build protons, neutrons, and countless other particles. But gluons behave differently from the force-carrying particles of gravity or electromagnetism. They interact not only with quarks but with each other as well, forming a dense, self-reinforcing web that traps quarks inside. This makes the strong force so intense that tearing a single proton apart would require energies far beyond anything humanity can produce outside of massive particle colliders. Without gluons, atoms, and therefore all matter, could never exist. In a very literal sense, gluons are the invisible threads stitching the universe together at its tiniest scales. Without the Higgs boson, mass itself would not exist. The Higgs boson, discovered in 2012 at CERN's Large Hadron Collider, completed the standard model of particle physics. It is tied to the Higgs field, an unseen energy field that surrounds every corner of space. As particles move through this field, they interact with it, and this interaction grants them mass. Without the Higgs field, particles like electrons and quarks would be weightless, and atoms, planets, and life would never form. The Higgs boson is a quantum ripple, an excited vibration, of the Higgs field, visible only in ultra-energetic collisions. Its discovery confirmed a decades-old prediction and earned François Englert and Peter Higgs the Nobel Prize. It also revealed a profound answer to a simple question: why does anything have weight at all? Empty space seethes with momentary virtual particles. Even in a perfect vacuum, space is never truly empty. Quantum field theory predicts that pairs of particles and antiparticles continually flash into existence, borrowing energy from the void before vanishing again. These virtual particles can't be seen directly, but their influence is measurable. They cause tiny shifts in atomic energy levels and create forces between objects in a vacuum, known as the Casimir effect. This constant flickering means empty space behaves more like a restless sea than a calm nothingness. The idea that nothing is full of brief, unseen particles is one of quantum physics' strangest yet most verified predictions. The quantum vacuum is overflowing with energy. All those fleeting virtual particles contribute to what's known as zero-point energy. Energy that remains even when a system reaches its lowest possible state. In theory, every cubic centimeter of empty space contains a staggering amount of this energy. Most of it cancels out or remains inaccessible, but we can still detect its influence in delicate effects, like atomic behavior and the expansion of the cosmos. In cosmology, some researchers believe dark energy, the mysterious force accelerating the universe, may be connected to vacuum energy. Yet here lies a deep puzzle. Theoretical estimates predict a vacuum energy far greater than what we observe. This massive discrepancy shows that we still don't fully grasp one of reality's most fundamental ingredients. Antimatter is matter's perfect, mirrored twin. For every particle, there exists an antiparticle with identical mass but opposite charge and reverse properties. When a particle meets its antiparticle, both disappear in a burst of pure energy. Antimatter was predicted by Paul Dirac in 1928 and soon discovered in cosmic rays. Today it's extremely scarce. Most of it vanished in mutual destruction shortly after the Big Bang. Why matter survived while antimatter almost completely disappeared remains one of physics' greatest mysteries. We can create antimatter in particle accelerators and even trap tiny amounts, but storing it is incredibly difficult, because it annihilates the instant it touches ordinary matter. Antimatter isn't just an odd scientific footnote. It carries real potential for future technologies, from medical imaging like PET scans to advanced propulsion concepts that might one day tap into its extraordinary energy density. Matter itself can be born from pure energy and then vanish back into it. Einstein's famous equation, E equals mc squared, reveals that mass and energy are simply two faces of the same essence. Under extreme conditions, energy can condense into matter, and matter can dissolve back into energy. High-energy collisions, such as those in particle accelerators or near black holes, can create particle-antiparticle pairs out of sheer energy. And when those particles meet their opposites, they simply annihilate into photons. This ongoing exchange between mass and energy unfolds across the universe, inside stars during the earliest moments of creation and throughout violent cosmic events. It reminds us that matter isn't a permanent, solid thing. It's a temporary form that energy takes before returning to light. Every particle is nothing more than a ripple in an unseen field. According to quantum field theory, the universe isn't built from little particles drifting in empty space. Instead, it's woven from fundamental fields that reach everywhere. Each type of particle is just a tiny vibration or localized disturbance in its own field. Electrons are ripples in the electron field. Photons are tremors in the electromagnetic field, and so on. Even when there are no particles around, the fields still exist, quietly saturating all of space. This view unifies matter and energy as two expressions of the same underlying fabric. It also shows that particles aren't miniature marbles at all. They're events, brief disturbances in something deeper and more fundamental. Wherever you are, these hidden fields surround you, shaping everything you see, feel, and experience. Quantum field theory merges particles and forces into one framework. Before QFT, scientists treated particles and forces as separate things, objects interacting through invisible pushes and pulls. But QFT revealed that forces are born from fields, and their influence is carried by particles. In electromagnetism, the electromagnetic field creates photons, which transmit the force between charged particles. The strong nuclear force arises from the gluon field, and the weak nuclear force from the W and Z boson fields. Even gravity may eventually be described this way, although a complete quantum theory of gravity still escapes us. QFT is one of the most accurate scientific frameworks ever built, with predictions tested to astonishing precision. It is our most powerful description of reality at the smallest scales. A single language that explains both the matter we observe and the forces that govern it. Even the emptiest space is alive with motion. If you picture the vacuum as cold, silent nothingness, quantum physics asks you to reconsider. Even without any particles, fields are never fully at rest. They tremble with constant fluctuations, spawning momentary virtual particles that disappear almost immediately. This restless backdrop exists everywhere, between distant stars, within atoms, even in the empty space of your own room. It is an energy that cannot be switched off. And though much of it remains hidden, it leaves measurable signatures in experiments. The realization that nothing is actually a vibrant, active medium changes how we see the universe. Space isn't just a blank stage where events occur. It's a participant, quietly molding the unfolding story in every moment. A perfect vacuum can even pull objects together. It sounds like something from a sci-fi tale. Place two uncharged metal plates very close to each other in a vacuum, and they slowly creep inward. This is the Casimir effect, a direct result of quantum fluctuations in the vacuum. The small gap between the plates allows only certain wavelengths of virtual particles to exist, while the space outside allows far more. That imbalance in pressure pushes the plates together. Though the effect is tiny, scientists have measured it in laboratories, proving once again that the vacuum isn't empty at all. While it has no practical use yet, the Casimir effect is a vivid reminder that quantum forces can rise out of what appears to be nothing, influencing the movement of real physical objects. Zero-point energy exists everywhere in the universe. Even when a system reaches its lowest possible energy state, with no heat, no motion, no light, it still contains a leftover amount of energy known as zero-point energy. This stems directly from the uncertainty principle. A field cannot have exactly zero energy because that would require knowing both its position and momentum with perfect precision. Though zero-point energy is minuscule on human scales, its presence everywhere means that across the vastness of the cosmos, it may sum to something unimaginably large. Some theories propose it might be tied to the elusive dark energy responsible for the universe's accelerated expansion. Whether that's accurate or not, zero-point energy stands as one of the clearest demonstrations that quantum physics insists empty space is never truly empty. What looks like a void can bend gravity and distort time. In Einstein's general relativity, mass and energy instruct spacetime how to curve, and that curvature directs matter how to move. If the vacuum carries quantum energy, then even nothingness can sculpt the universe's geometry. This suggests that quantum effects may subtly shape gravity and perhaps time itself. In principle, the density of vacuum energy could influence how the cosmos expands, how galaxies emerge, and even how time behaves under extreme conditions. The true nature of this interplay remains hidden, partly because merging quantum theory with gravity into one unified description is still among physics' greatest challenges. Yet the secret to cosmic evolution may be concealed within the fabric of empty space. Powerful fields can distort the very character of the vacuum. It may seem permanent and unchangeable, but under extraordinary circumstances, it can shift and respond. Extremely strong electric or magnetic fields can polarize the vacuum, aligning its virtual particles in ways that modify its behavior. In theory, if these fields become intense enough, they could even cause the vacuum to rupture, creating real particle-antiparticle pairs directly from energy. This process, known as vacuum decay, has never been directly observed. The required field strengths exceed anything humanity can produce, yet its effects emerge naturally from quantum electrodynamics. Such behavior shows that the vacuum is not a silent background but a lively, reactive medium capable of answering its environment in unexpected ways. Black holes glow by drawing energy out of empty space. Black holes are famous for allowing nothing to escape, not even light. And yet quantum theory predicts that they can slowly emit energy through Hawking radiation. Near the event horizon, vacuum fluctuations constantly spawn virtual particle pairs. Normally they annihilate instantly, but at the black hole's edge, one particle can fall inward while the other escapes. To an outside observer, it appears as though the black hole is radiating, gradually losing mass. This emission is unimaginably faint for large black holes, but it carries a deep message. Quantum physics reveals that even the darkest, most trapped regions of the universe are not entirely black. The energy of emptiness may be stretching the universe apart. In 1998, astronomers discovered that cosmic expansion is speeding up. Its cause remains unknown, but a leading explanation is dark energy, a form of energy built directly into the fabric of space. If dark energy exists, it behaves much like vacuum energy, applying a steady outward push. Over billions of years, this pressure could pull the universe so wide that distant galaxies drift permanently out of reach. The idea that the fate of the cosmos might hinge on the energy of empty space is one of the most haunting discoveries in modern science. The real nature of the quantum vacuum is still hidden. We can describe it with mathematics, measure its influence in precision experiments, and even link it to cosmic scale events. Yet we still don't truly know what it is. Is it a physical medium like an invisible ocean filling the universe? Is it simply a property of fields that remain present even without particles? Or is it something stranger, perhaps connected to the universe's very beginning? The vacuum lies at the crossroads of quantum mechanics, relativity, and cosmology, three pillars of physics that still resist complete unification. Until we fully understand it, the emptiness between the stars will remain among the deepest and most mysterious features of reality. Quantum computers can think across multiple realities at once. Unlike classical computers, which store information in bits that are either 0 or 1, quantum computers use qubits, units that can exist in superpositions of both 0 and 1 simultaneously. This lets them explore many potential answers at the same time, almost as if they're evaluating possibilities across parallel realities before choosing an outcome. The power of this approach increases exponentially with each additional qubit, allowing some problems that would take classical machines millennia to be solved in moments. Quantum computers are still young technology, battling errors and instability, yet even now they hint at a future where challenges in chemistry, cryptography, and optimization could be conquered with astonishing speed. It isn't magic. It's the quantum logic of probability and interference, harnessed in a form classical computing can't match. Qubits can hold multiple answers in a single instant. A qubit isn't fixed into one definite state until it's measured. Until that moment, it carries a blend of possibilities, both 0 and 1, each weighted by probability. This property is what gives quantum computers their extraordinary potential. With only a small number of qubits, you can represent a staggering range of possible combinations at the same time. When a quantum algorithm runs, it steers these probabilities in a precisely orchestrated pattern so that incorrect paths cancel out and the right answer remains. It's like searching an entire library simultaneously instead of checking one book at a time. The challenge is that measurement collapses a qubit state. So crafting algorithms that pull out meaningful results from this fragile superposition remains one of the core hurdles in quantum computing. Entanglement supercharges quantum computation. Entanglement isn't just a strange oddity. It's a powerful resource. In quantum machines, entangled qubits share correlations that classical bits can never achieve, allowing operations on one qubit to instantly affect its partners. This lets quantum computers handle complex tasks more efficiently, linking far-flung parts of a problem without transferring physical data. Entanglement is also essential for error correction, helping detect and repair issues without directly probing a qubit's delicate state. Without entanglement, quantum computers would lose most of their unique edge over classical hardware. It's the unseen thread holding their logic together, giving them the strength to tackle challenges far beyond today's fastest supercomputers. Certain quantum algorithms could solve problems almost instantly. Some algorithms are so powerful that, in theory, they could break problems that would stump classical computers for ages. A well-known example is Shor's algorithm, which can factor enormous numbers exponentially faster than the best classical techniques, an ability that could disrupt many modern encryption systems. Another is Grover's algorithm, which speeds up searching through unstructured data in a way no classical method can match. These algorithms don't make quantum computers faster at everything, but for the tasks they're designed for, the advantage is overwhelming. This is why governments, tech giants, and researchers are racing to build usable quantum processors. The first to succeed will unlock computational abilities that could reshape security and technology alike. Quantum cryptography creates secrets that can't be broken. Classical cryptography relies on problems that are difficult to solve, but a sufficiently powerful computer could, in principle, crack them. Quantum cryptography, however, uses the laws of physics themselves to guarantee protection. The most famous approach, quantum key distribution (QKD), sends encryption keys encoded in the quantum states of photons. Any attempt to intercept them inevitably disturbs these states, exposing the intrusion instantly. This makes secure communication possible even through channels an attacker can fully watch. Quantum cryptography has already been demonstrated in real-world networks, including satellite links, and may one day protect financial systems, government data, and personal information with unmatched security no classical method can offer. Quantum sensors detect the faintest whispers of change. By leveraging quantum effects like superposition and entanglement, quantum sensors can measure things such as time, motion, and magnetic fields with astonishing accuracy. They're so sensitive they can pick up changes far too small for any classical instrument. Variations from tiny gravitational shifts, subtle signals in the brain, or even hints of dark matter interactions. Some designs rely on clouds of ultra-cold atoms or nitrogen vacancy centers inside diamonds to reach this precision. In the years ahead, quantum sensors could transform navigation, medical diagnostics, and geological exploration, revealing new insights into the human body and the Earth itself. Superconductors allow electricity to flow forever with no loss. Normally, electric currents face resistance, wasting energy as heat. But in certain materials chilled to extremely low temperatures, resistance falls to zero. This is superconductivity. In this phase, electrons pair up and move without losing energy, potentially forever. The effect is purely quantum, emerging from countless particles acting as one coordinated wave. Superconductors already power MRI machines, particle accelerators, and magnetic levitation trains. But achieving room temperature superconductivity would revolutionize energy systems, eliminating wasted power and enabling entirely new technologies. Quantum networks could connect computers worldwide. Just like classical devices use the internet today, future quantum computers could be linked through quantum networks. These systems would rely on entanglement and quantum teleportation to transmit information in ways that can't be intercepted without detection. Building such a network requires maintaining entanglement over long distances, something scientists are already exploring through optical fibers, satellites, and quantum repeaters. A fully developed quantum internet could enable ultra-secure communications, shared quantum computing, and new types of sensing across vast regions, turning the entire planet into one interconnected quantum web. Atomic clocks keep time so precisely that they barely drift in billions of years. The most accurate timekeepers on Earth are atomic clocks, which use the natural vibrations of atoms, often cesium or ytterbium, as their ticks. In advanced designs, atoms are cooled to near absolute zero and held steady by lasers, allowing their oscillations to be measured with incredible accuracy. The best atomic clocks would gain or lose less than a single second across the entire lifetime of the universe. Such precision isn't just a scientific luxury. It's essential for GPS systems, global communication networks, and countless experiments. Quantum breakthroughs are pushing this accuracy even further. So far, in fact, that atomic clocks may soon detect slight shifts in the flow of time caused by tiny differences in gravitational height. Quantum technology is already transforming science. While quantum computers usually capture the spotlight, other quantum tools are quietly reshaping research and industry. Quantum sensors are revealing hidden structures underground, quantum communication links are securing early test networks, and quantum simulators are helping researchers study complex molecules and new materials. These systems aren't fantasies from science fiction. They are real technologies built from the principles of quantum mechanics, and they're expanding what we can do right now. As these tools continue to evolve, they will likely influence everything from climate prediction to medical breakthroughs, giving us new ways to explore and reshape our world. The quantum revolution isn't a distant dream. It's already unfolding, silently altering how we understand reality. The Copenhagen interpretation says reality isn't definite until measured. The Copenhagen interpretation, developed in the 1920s by Niels Bohr and Werner Heisenberg, remains one of the most widely taught explanations of quantum mechanics. It proposes that a quantum system has no definite properties until it's observed. Before measurement, it exists in a superposition, an overlap of every possible outcome. The act of observing forces the system into one specific state, collapsing the wave function. This viewpoint works beautifully in experiments, yet it's deeply unsettling philosophically. Does reality truly depend on observation to become definite? Or is wave function collapse simply a mathematical tool we use because we cannot track every quantum detail? The Copenhagen interpretation leaves these mysteries unresolved, embracing uncertainty as a core feature of the universe rather than a flaw in our understanding. The many worlds view suggests every outcome actually occurs. Proposed by Hugh Everett in 1957, the many worlds interpretation avoids wave function collapse completely. It claims that whenever a quantum event could have several outcomes, each possibility happens, but in different branching universes. If a particle might move left or right, the universe divides, creating one version where it shifts left and another where it moves right. In this interpretation, reality becomes an endlessly growing tree of possibilities, filled with countless versions of us living through different stories. Although it keeps the equations of quantum mechanics intact and removes the mystery of collapse, it introduces immense questions. If all outcomes occur somewhere, what does it mean to choose? And could these parallel branches ever interact or be detected? Pilot wave theory gives particles hidden paths to follow. Pilot wave theory, also called Bohmian mechanics, offers a more deterministic view of the quantum world. It argues that particles always have specific positions and velocities, guided by a pilot wave that evolves according to the Schrödinger equation. The strange interference patterns seen in experiments arise not because particles are spread out in space, but because this guiding wave shapes their trajectories. Pilot wave theory matches all predictions of standard quantum mechanics, but adds hidden variables, unseen details that dictate precisely how each particle moves. It's attractive to those uncomfortable with randomness, although it requires accepting non-local effects, where distant events influence one another instantaneously. Collapse theories say quantum states can end themselves. Collapse theories suggest that superpositions don't last forever, even without measurement. They eventually resolve into a single outcome on their own. In these models, quantum states evolve normally but carry a tiny probability of collapsing spontaneously at any moment. For small systems like atoms, this probability is extremely low, allowing superpositions to survive. For larger systems, collapse happens so rapidly that we never encounter superpositions in everyday life. These theories try to clarify why we don't witness quantum oddities at everyday scales without relying on conscious observers or branching universes. Experiments are already underway to probe collapse models by searching for faint, random bursts of energy that would indicate a spontaneous fall of the wave function. Decoherence explains why quantum strangeness vanishes in large objects. Decoherence isn't a separate interpretation, but a real physical mechanism that helps us understand why quantum behavior fades as systems grow. When a quantum object interacts with its surroundings, air particles, light, vibrations, information about its state leaks into countless environmental degrees of freedom. This effectively measures the system, wiping out delicate superposition patterns and making it act more like classical matter. Decoherence happens astonishingly fast for everyday objects, which is why we never see them in visibly mixed states. While decoherence describes the shift from quantum to classical behavior, it still doesn't resolve the measurement problem. It leaves untouched the deeper issue of how a single outcome is chosen from many possibilities. The measurement problem still perplexes physicists. At the very center of quantum theory sits this puzzle. How does a superposition transform into one definite outcome when observed? The equations describe a wave function evolving smoothly, yet say nothing about the abrupt collapse into a specific result. Is this collapse a genuine physical event or simply a change in what we know? Interpretations from Copenhagen to many worlds to collapse models each offer different explanations, but none are proven. The measurement problem isn't just abstract philosophy. It reaches into the nature of existence itself and whether the world has definite properties when unobserved. Could human awareness determine reality's outcome? A few interpretations, often considered controversial, suggest that consciousness might play a role in collapsing the wave function. In this perspective, it isn't only the physical act of measurement that sets an outcome, but the presence of an aware observer. This observer effect is often exaggerated in popular culture, yet the core idea traces back to discussions by physicists like John von Neumann and Eugene Wigner. While most scientists today favor purely physical explanations, the notion that the mind could influence foundational processes is undeniably intriguing. Testing such ideas is extremely difficult, but the question persists. Does our awareness help shape reality simply by noticing it? Quantum logic doesn't always follow ordinary reasoning. In classical logic, statements are either true or false. There's no in-between. But in the quantum realm, logical structure behaves differently. A property can be partly true and partly false at once, depending on how it's measured. The sequence in which you measure different quantities can completely change the result, something impossible in classical physics. Quantum logic emerges from the mathematics of Hilbert space, where events are not strict yes or no facts but probabilities that can overlap and interfere. This break from everyday logic is one reason quantum mechanics feels so alien. The universe doesn't just behave strangely, the rules we use to describe it must be rewritten. The universe may be fundamentally random at its deepest level. In quantum mechanics, certain events have no cause that can be predicted ahead of time, no matter how perfect the information in hand.